So in the context of our larger outline for this section, last week we looked at in the last video, we looked at definitions of concentrations, ratios, and standards for stable environmental isotopes, focusing on the water molecule. And this video is part 2, where we're going to look at isotope reactions, specifically equilibrium fractionation, the effects of temperature on fractionation, and Rayleigh distillation of isotopes. So as a quick review, our O18 and deuterium are constituent parts of the natural water molecule. And so this is what allows us to fingerprint water. It's an idealized tracer without, excuse me, conservative tracer. And the variation in isotope signatures of water occur naturally in precipitation events. So it's a conservative tracer. At ambient temperatures, isotope ratios will only change due to either mixing of different water sources or fractionation, which we're going to define in this set of slides. So we're going to discuss that in detail. And there's no additional chemical reactions that will influence the differences in concentrations we see. So we've seen this slide in our earlier video, just showing us on the left-hand side the different processes by which water moves around as a function of the hydrologic cycle. And all those physical processes potentially influence the isotopic signature of water as it travels. And so on the right-hand side, we actually see typical signatures of delta O18 in this example, and how they vary across these different processes. And we'll come back to this, specifically talking about evaporation and condensation, which changes the isotopic ratios through this process of fractionation. We can also get mixing of different sources of water. So for instance, in the upper atmosphere or in the atmosphere, we might have different sources of vapor that mix together and change the isotopic signature. We can also get condensation, that's changing the remaining vapor. And so that would be one example of how these physical processes change the isotopic signatures of water at different locations in the hydrologic cycle. Again, a brief review from the last video. So stable isotopes of an element like hydrogen and oxygen behave the same chemically. They are the same element, so they participate in all reactions as defined by the individual element, but their slight mass difference affects bond strengths such that they accumulate preferentially on one side or another of a reaction. And specifically, we're interested in condensation and evaporation as our reactions of interest. So this mass-dependent partitioning, or what we term fractionation of isotopes, is what makes them good tracers of the origins and reactions of for water and solutes. So for our hydrologic system, the distribution of isotopes is controlled by the interplay then of two processes: the fractionation of isotopes during physical reactions of evaporation and condensation, and then the distillation of isotopes from the reactant reservoir as the reaction proceeds. And we're going to see an example of this later if we think about distilling water from a pond in our landscape, for example. So we'll put some strong examples to this terminology that you're learning about. So these are the two processes that work together to partition isotopes into different reservoirs that then will influence the isotopic signatures of water. So the textbook, when we're talking about fractionation, the textbook uses a simple analogy of building a stone wall in presenting this concept of fractionation. So fractionation, that mass balance partitioning, can take place under equilibrium conditions. So here we're really just talking, when we say equilibrium conditions, we're talking about when the distribution of isotopes we're talking about having equal rates of forward and backward reaction. So we can think about our reaction being evaporation and condensation of water. So when we talk about thermodynamic equilibrium, we're simply looking at evaporation and condensation being equal in magnitude. So that's happening, they're happening at the same time and they're equal. So the equilibrium fractionation is the mass-dependent process at the level of a physical or chemical reaction that partitions isotopes on one side or the other of a reaction. So our fence, back to our fence building analogy here, if we're building a fence from a field of stones, the reaction is, the equivalent of our chemical reaction here is gathering and placing the stones from the field. And we're doing that by pulling rocks from a reservoir, that is the field. So that would be referred to as the reactant reservoir, and we're putting them in the fence. So the reservoir is the field of stones, someone's building the fence, and of course is looking at stones of different sizes, but they're preferentially selecting the big ones because they make a stronger fence. So as they work, they're removing some of the stones from that reservoir, the field, and replacing them with others that fit better. So the fence has a high abundance of big stones. And so that preference for big stones, pulling those from the field, is the fractionating process of the heavy and light stones between the field and the fence. So the fence is becomes enriched in heavy or big stones compared to the reservoir of stones in the field, which become depleted in the big stones. So our equilibrium fractionation here is changing, or is here we've got this image where we can think about the O16 being the lighter element of oxygen, the O18 the orange. And so when we're talking about chemical or equilibrium fractionation, we're talking about the various processes that sort light elements from heavy elements, and as a result change the delta O18, that isotopic ratio in the reactant reservoir and the product reservoir. So this term equilibrium fractionation is really referring to that partitioning of isotopes between substances during reactions such that substances have different isotope ratios. It's a sorting of light from the heavy versions of an element, and the isotope ratios change during transition from one phase or molecule to another. And again, here we're particularly interested in this reaction between liquid versus vapor, condensation or evaporation of water. So as an example of equilibrium fractionation, just to kind of illustrate the point here that this net partitioning of isotopes is very small, but it's measurable and it's reproducible, and that's what supports the ability to actually use these as a tracer. So the partitioning of isotopes in a physiochemical reaction is more subtle than the analogy, of course, of building a stone wall. If we look at this example that's provided on page 99 from Clark, the concentration of delta O18, the concentration of O18 in water in units of parts per million is about 2,000 parts per million. And in ice, it's about 2006 parts per million. So the difference here between 2,000 parts per million and 2006 parts per million. So we have more heavy isotopes, a larger concentration of the O18 in ice compared to liquid water. If we take and look at the difference, that's 6 ppm, and divide through by the concentration in water of 2,000 ppms, we get an answer of 0.003 or 0.3%, or we can convert that into per mils as a 3 per mil enrichment of the O18 in ice compared to that of water. So for ice, we have slightly more O18. It's enriched in O18 compared to water. So it takes more energy to break the bonds of O18 to melt it from ice to water compared to a molecule with O16. So we have less O18 in water compared to ice. And we can express this difference in the ratio of O18 to O16 in ice. So just changing our units here to 2.006 times 10 to the minus 3 compared to that of water, which is 2 times 10 to the minus 3. And if we divide that, or we use that ratio, then that gives us a fractionation of 1.003. I'll speak a little bit more about the fractionation here term, but this is not much of a difference, but it is measurable and reproducible, as I mentioned at the beginning. So here we can consider evaporation and condensation as our example of a physical reaction. The equilibrium fractionation factor alpha, which we're going to define, establishes the isotope ratios in components of isotope exchange reactions. And so here we can see this reaction of evaporation and condensation in our equation here, where we've got H2O water and vapor. We've got that on either side. So as the reaction approaches equilibrium, the transfer of reactants on the left to the products on the right is matched by the reverse reaction, such that some water is evaporated to vapor and some vapor is condensing to water. And if we add isotopes to the reactions, which we see here in the lower equation, there's going to be a forward and a backward exchange of isotopes until there's an equilibrium distribution with either the reactant on the left or the product on the right having more of the heavier isotope. This preferential partitioning or fractionation that we're using alpha here, our fractionation factor, to describe, the alpha values are very close to 1, and this is because the partitioning of isotopes between compounds is very minor. So the equilibrium fractionation factor defines the equilibrium condition, just like an equilibrium constant for a geochemical reaction. It's simply, so the equilibrium fractionation factor, alpha, is simply the ratio of the isotope ratios in the two reacting phases. And as I mentioned, the isotope fractionation factor are, for the most part, very close to 1, and this is because the partitioning of isotopes between compounds is very minor. The fractionation factor here is usually expressed as the isotope abundance ratio in the product on the right side, or the right side of the equation, over the abundance ratio in the reactant on the left side of the equation. And so here we can see the alpha product reactant is equal to the ratio of isotopes in the product divided through by the ratio of isotopes in the reactant. And then on the right-hand side, you can see an example for delta 18 for water and vapor. So the product being water in this example here, and the reactant being vapor here. So this actually is an example from condensation, not evaporation. If we're saying the product is liquid water and the reactant is vapor. So we've got a few examples to speak a little bit more about the fractionation then. So if we think about water on the left-hand side of this equation, where water is being evaporated from the ocean, it's going to be depleted in deuterium, the heavier isotope of hydrogen, and O18, the heavier isotope of oxygen, relative to its source or reactant, the ocean. And then when we actually, you can see on the right-hand side, as that water is is being condensed from the cloud to land, we've got, it's going to be, the cloud itself is going to lose water it's going to become depleted in deuterium and O18 relative to the precipitation that's being generated. The heavier isotopes are going to partition out first, or preferentially, and enriched, and the precipitation is becoming enriched in deuterium and O18 relative to the vapor. So precipitation will be depleted in O18 relative to the standard water. We often have a negative value here, but remember that when we're using these depleted enriched terminology here, it's relative to, for instance, a source or a starting water. So we just have to keep that in mind as we use these terms. So a rule of thumb related to our fractionation as we understand it, lighter molecules are going to react faster. So O18 and deuterium content of water changes through fractionation associated with these phase change processes. So in the case of evaporation, the vapor that forms is going to be lighter than the water from which it's formed. And the molecules of water are held together by weaker hydrogen bonds. And so here I'm referring to page 101. We think about which bonds, hydrogen bonds, are stronger. The H2O with delta O18 or the H2O with delta 016. The atoms with greater mass form slightly stronger bonds. So the heavier isotope is generally enriched in the more condensed phase. So we've got slightly greater hydrogen bond strength for the heavier isotope, the H2O 18, than for the lighter isotope, the H2O 16. So it's the O16 bonds that are going to be more easily broken during evaporation. Easier to break the bonds means it takes less energy for the O18 to be evaporated. So we're going to have less of the O18 in the vapor phase, relatively speaking. So water is going to be isotopically enriched over its vapor in the heavier isotope. Similarly, O18 is going to be more enriched in ice than in water. And we've seen that example earlier. In terms of condensation, then liquid forms is heavier than the vapor from which it forms.